We're going to look at some musical ratios, and we'll also look at how those musical ratios were used in other fields other than music. Now, we've already looked at Pythagoras and his work with music. Pythagoras used his monochord to find some lengths of a string that would produce pleasing sounds. Those lengths were described using some ratios, and he found these lengths simply by strumming the string and listening to it and deciding by ear what seemed to sound the most pleasing to him. Now, there were others after Pythagoras who decided that perhaps there were some other notes that were also pleasing to the ear, but they found them in different ways. Plato actually used mathematics to come up with some notes that were in between the ones Pythagoras discovered, and he decided that these notes were also pleasing, but he used mathematics to find his notes. Now, here's the major diatonic scale that we use today. If you look within that scale, you'll still see those Pythagorean ratios. But you'll also see some ratios in between those Pythagorean ratios. Those are the ratios that Plato was looking for by looking for mathematical patterns. For example, if you look at the pattern from the C to the D to the E, or you look at the pattern from the F to the G to the A to the B, what you see is geometric progressions. Now, Pythagoras and the Pythagoreans believed that numbers could be used to describe the meaning of everything that we know. That means everything on the Earth and everything in the solar system. So when they looked at things like how far were the planets from the Earth, they decided that those distances could be described using these special ratios. So what the Pythagoreans decided was that everything that was on the Earth was harmonious, and everything that was in the solar system was harmonious because of the numerical relationships between those things. The musical ratios were applied to other fields, and one field that you especially see these ratios used is in the field of architecture. So when an architect would design a building, they would decide on the size of the different parts of the building according to the ratios that they thought were beautiful. Now let's look at an example of how that might have been done. Suppose that an architect wanted to design a window for a building, and that window was supposed to be in the shape of a rectangle surmounted by a semicircle. So the architect wants to decide what size to make the rectangular part of the window. If the architect wanted that rectangular part of the window to be in a ratio that was equivalent to a perfect fourth, they would have to decide how long or how wide that part of the building needed to be. And then they could use that value to find the other dimension that they were looking for. So let's suppose this window is supposed to be shorter along the horizontal dimension and longer on the vertical dimension. And the horizontal dimension measures 4.5 feet. We want to know how long this longer vertical dimension is. So if we look at the ratio described by a perfect fourth, we're comparing 3 parts to 4 parts, 3 being the shorter part, 4 being the longer part. So we can write a proportion that says 3 is to 4 as 4.5 is to x. So now if we cross multiply and solve the equation, we'll find out that the value for x that makes the proportion true is 6, which means that vertical part of the window, the vertical part of the rectangular part of the window, needs to be 6 feet tall. Next, we're going to look at a couple of constructions. This one is constructing a line parallel to another line, and that line will contain a point. So here's our line and a point that's not on the line. We want to construct a line that is parallel to this line but that goes through this point. So the first thing I'm going to do is, remembering that we can only put the point of the compass on points or intersections, I'm going to put the point of the compass on this point and make an arc through the line. Now I'm not going to change the setting on the compass, but I've created a new intersection and I can put the point of the compass there and make another arc. Now I'm going to move to that intersection and make an arc up here and return to the point and make one more arc. Now if I take a look at that point that we started with and the intersection that we just finished drawing, I can draw a line through both that point and the intersection, and this line is parallel to the line that we started with and it contains point P. Our last construction is to subdivide a line segment into a number of congruent segments. So here's line segment AB, and let's say we want to subdivide that into 3 congruent parts. So what I'm going to do is take my compass and set it actually any setting I want it to be at. And I'm going to use that setting as a way to divide a different line segment into 3 congruent parts. So I'll draw a line segment from point A as long as I want it to be, but what I'm going to do is take this line segment and pick this arbitrary measurement and use that arbitrary measurement to subdivide my new line segment into 1, 2, 3 congruent parts. Alright, let me call this intersection C so we know what we're talking about here. Now I'm going to take my straight edge and draw a line segment from C to B. Now the next thing I want to do is construct a line segment that's parallel to this one, but that contains this point. So we've already talked about how to construct parallels. We're basically going to do that same construction. So I'm going to take this compass, I'll put it back the way it was. I'm going to take that same measurement, mark it off here, and here, and here. And that intersection, when I connect it up with this point, which I probably should have named, so I will name it, let's call that point D, will now give me a parallel. Now if I construct a parallel to this through this point, I'll have one more parallel here. Let me call that point E so we know what we're talking about. Alright, so remember I've still got this measurement here. I've got that same measurement here and here and here. And it coincidentally looks like it's intersecting pretty much at that bottom line segment, but that is just a coincidence. And then I'm going to connect up these intersections. So this line segment is parallel to this one's parallel to this one. Now since we originally divided this into 3 congruent parts and these are all parallel, that means we now have, if we look at these intersections, let me call that F and G, we now have line segment AB divided into 1, 2, 3 congruent segments. So as usual, what you need to do is read the book and get some additional information out of that. And you also need to practice these constructions and do the homework to make sure that you're prepared before you come to class.